Hey guys, today we are talking about simple machines. Now, when we talk about simple machines, first, so far in this unit, we have been talking about rotational stuff. So, we've been talking about uniform circular motion, centripetal acceleration, and centripetal force. Well, what we're talking about today with simple machines has absolutely nothing to do with any of those past things, except that it maybe has a little bit of something to do with torque, but really not all that much. This is one of those topics that would really go very nicely in our unit on work, but instead it ended up being placed in the textbook with our section on torque. And so we'll talk about it today. In the context of torque and work. So before we get started today, you do need to have a pretty good understanding of torque. Well, and torque, and definitely especially of work, because that'll play a lot into what we're looking at today with simple machines. When we talk about simple machines, there are 6 types of simple machines. There's a ramp, a screw, a wedge, a wheel and axle, a lever, and a pulley here that I'm blocking, but I'll move my face out of the way in a moment. And we're going to talk through each of these 6 types of simple machines. Before we do that, a few things first. When I think of machine, I think of a thing that's happening in a factory that's going and all this kind of stuff is happening. That is not what we talk about when we talk about simple machines. Keyword here is simple. These are the kinds of machines that a caveman would have invented and said, but not quite as fire. Like fire was probably a little bit more than simple machines. But simple machines is something that some caveman would have come up with and been like, this is awesome. So our overall arching idea about simple machines is that simple machines make work easier by trading force for distance. Simple machines make work easier by trading force for distance. They don't make work less, but they do make that work easier by trading force for distance. Now, before we get started here, you definitely have to know that that work is equal to force times distance. That's going to be a key component of today, and it's also helpful to know and understand that work is a transfer of energy. So, simple machines make work easier by trading force for distance. Let's take a look at a ramp here. Suppose that I had a block and I needed to move this block up into the back of a moving truck. Now, suppose that this block was actually a refrigerator. Let's make things extreme. And suppose that I need to bring this refrigerator into the back of the moving truck. Now, one thing that I could do is I could wrap both my arms around this refrigerator and I could lift it straight up into the back of the moving truck and bam, that would be done. Or I could take that refrigerator, I could set it on a ramp, and I could slide it up a ramp into the back of the moving truck. In both of these situations, if I asked you which one transfers more work, sliding a refrigerator up a ramp or lifting a refrigerator straight up into the air, you would say, well, both, Miss Wilson. They take the same amount of work both ways. But even though they take the same amount of work, they do that work differently. Notice, if I were to lift a box straight up, that would require, or if I were to lift a refrigerator straight up, for example, sorry. Oh, don't do that. Okay. If I were to lift a refrigerator straight, this is embarrassing. If I were to lift a refrigerator straight up like this, it would require a whole lot of force because that thing is heavy. But I wouldn't have to lift it that far. I would only have to lift it a distance about that big, a little delta x here. Ooh, I should really be working my little pen here because my pen will do better. We'll finish out in the marker and then we'll switch to a pen. But if I had to slide my refrigerator up the ramp, well, it wouldn't take as much. Oh, I need to change my color actually. It wouldn't take as much force. Like I wouldn't have to push on this thing as hard. I could push on it less hard, but I would have to push it for longer because I would push it this hard, much less hard, but I would have to push it up the whole length of the ramp up to the tippy top like this. So my delta x that I have to push for would be much bigger, but my force would be much smaller. In both situations, I do work. I apply a force for a certain amount of distance. But the amount of work that I do in each situation is distributed differently. At the end, the refrigerator has gained the same amount of gravitational potential energy both ways, but it's accomplished that task differently. We call the way that I do it with the ramp, the amount of force that I put in and the amount of distance that I go and the total amount of work that I put in, we call this the input. It's the input work, which is the input force times the input distance. So you could put little subscripts of in on all of these. And over here, what I get out, which is basically what I would accomplish if the ramp wasn't there, the task that the ramp is doing for me, what the ramp is allowing me to accomplish, this is what I call my output work. It's the work that I get out, which is the force that I would have to apply if the ramp wasn't there times the distance I would have to go if the ramp wasn't there. So the output is what the ramp helps me to accomplish. It's the task that the ramp helps me to accomplish. The input is the force that I put in and the distance that I put in for that particular ramp. And that's an example of a ramp. Let's take a look at our second example, which is a screw. A screw, when I'm talking about a screw, I really am talking about the difference between like a nail and a screw, like the things that go into wood. Now, if I wanted to, sorry, let me move this guy out of the way here so that we can go over here. Oh gosh, come here. You go over here. Yes, and rest there. That is a great place for you. Okay, if I wanted to connect some pieces of wood together, I could take a nail. And I could hammer that nail into the wood. Now, hammering the nail into the wood, that takes a very big force. It takes a big force from that hammer going onto the nail. But that force happens for just the distance that the nail goes into my wood. Here's my delta X. But a screw is a little bit of a game changer. And let me show you why. Actually, I forgot my screw. So let me go get my screw really quick. And then I can show you how a screw works. One moment. Okay, here's a very lame demonstration for you. Here I have a pencil. Oh gosh, one second. Here I have a pencil, and I have taped an inclined plane to my pencil. Do you see that this is an inclined plane? It's just a ramp. Ramp and inclined plane, same thing, synonymous. I take a little inclined plane like this. I am going to take that inclined plane, and I am going to wrap it around my pencil. Like this. And you can see, if I wrap an inclined plane around a cylinder, I get a screw. A screw is just an inclined plane wrapped around a cylinder. So here's why it makes your life easier. With a hammer and a nail, you would have to hit this nail with a lot of force, but you'd only have to hit it for this distance. But with the screw, what you're going to do instead is you're going to apply a twisting force here. And that force is going to be much smaller. It doesn't have, when you're twisting your screwdriver, you don't put in as much force as you put in with a hammer and a nail. So that force is much smaller. But the distance here, you're going to make that wood, instead of that wood going from the bottom straight up to the top of the nail, you're going to make that wood go up the whole little path of this inclined plane all the way up to the top. It's like the wood is taking an inclined plane path all the way up to the top of the screw. And so instead of just going straight in, you're taking a much longer route to get it in there. You're taking an inclined plane kind of route. And so you have less force, but a much bigger distance that you go. In both cases, you do the same amount of work because you either do a small force times a big distance or a big force times a small distance. But in this case, this is our input with the simple machine. Notice that the simple machine trades force for distance, which is what all simple machines do. It takes a big force and it turns it into a big distance so that your force can be smaller. So that's my input over here. My output, which is what I would accomplish, which is what I would accomplish without the simple machine, or what I would have to do without the simple machine. It's what the simple machine helps me do, is a bigger force times a smaller distance. But you'll see that the input and the output both are requiring the same amount of work. Next, we're going to take a little look at a wedge. A wedge is really just two inclined planes stacked back to back like this. Now let's say that I gave you a log and I said, can you grab this log and tear both ends in half with your bare hands? You would say, Miss Wilson, that's challenging. But if I said, hey, here's an axe, then you could take that axe and you could swing it down and you could split the wood using an axe. 1 second here because I gotta pause and then we'll come back in a little bit. 1 moment, please. Okay, so
Cheers to the main office.
little announcement there. So for splitting the wood in half with an axe, when you take that axe, if I hold it back like this and I swing it down, when you're looking at the head of that axe, you'll see that the bottom part, the pointy part, comes to a point like this, and the top part, the head of the axe, is a little bit wider.
The key to the room if you're still in the building.
Okay, the head of the axe is a little bit wider, and then the bottom of the axe is sharp and skinny like this. This is a wedge. A wedge is a simple machine that's fat at the top and skinny at the bottom, and it's basically just two inclined planes stacked back to back. Do you see this is one inclined plane here, and this is the other inclined plane here? You'll see the same thing if you look at your kitchen knife. Your kitchen knife looks kind of something like this, where it's skinny at the bottom, and then it's wider up at the top. And anything that we use to cut stuff a lot of times is basically a little wedge. Now, here's the idea of a wedge. Let's say that I wanted to take this end of the log and this end of the log, and say that I wanted to divide them apart so that they were this far apart like this. That's my delta x. Well, one thing that you could do is if I said, hey, can you split this log in half? You would say, okay, and you would apply a force times a distance to split that log. Now that force that you would need to apply would likely be a pretty big force here in order to get that log to split in half. So you could apply a pretty hefty force, or you could use a wedge. If you use a wedge, instead of just taking those two pieces and making them go apart from each other like immediately, what you do is you help them to go apart from each other gradually by making each part of the wood go up an inclined plane. So this part of the wood goes up in a little inclined plane like this. And this part of the wood goes up a little inclined plane like this. And so each part of the wood goes up a little inclined plane. When each part of the wood goes up a little inclined plane, then it's gradually going to go until eventually the distance apart is the distance that you want, until eventually it's split this far apart. But do you see that it makes that journey more gradually, so that instead of just going a straight delta x all of a sudden, it goes a delta x first that's a little bit bigger. That means because it's going to accomplish this same delta x more gradually, you need less force to make it happen. It still takes force when you swing an axe to split a piece of wood, but it takes less force to split it when you got two inclined planes helping you, and it takes more force when you're just using your bare hands. So this over here is our input. That's what you put in with the help of your wedge here. It's the distance, which is the length here that it's traveling, times the force that you apply, versus the amount of your output, which is the amount of force that you would have to apply to that axe times the distance apart that you would pull those two pieces of wood. Next is a wheel and axle. Now, you don't know much about wheel and axles because you live today, and if I asked you to get a cup of water, then you would go to the sink and you would get yourself a cup of water. But not so in the day. Back in the day, the little people of the world had to go and bring their bucket of water to the well. And when they brought their bucket of water to the well, they would lower their bucket of water into the well, and then came the challenging part, because then they had to lift the bucket of water out of the well, and when it's full of water, that bucket is heavy. So what they did is they invented the wheel and axle to help the little children who were all carrying their buckets of water. Wow, just so many announcements. What fun. Now they invented the wheel and axle to help all the little children to pull their buckets of water out of the well. Now here's the idea. You have this axle here, this shaft like this, and then you have a rope wrapped around it. And the idea was that as you turn this little axle here, as you turn it in a circle, then it's going to gradually raise your bucket up. Now, if you wanted to turn this little guy here to raise up the rope as the rope winds around the axle, you would have to turn it like this. Let's say that you give it a little half turn like this. You'd have to turn it this much, a little delta x, but doing that is hard. It takes a lot of force, almost as much force as it would just take to lift the bucket, but you don't have to turn it for very far. But all the little children of the world started to complain about how hard their lives were and how they had to go all the way to the well, and then once they got to the well, it was really, really hard to pull up the bucket of water, so they invented the wheel and axle. Basically what they did, oh gosh, let me move this guy out of the way. Again, go away. You got it. Wait, you're almost there. All the way up, out of the way. Yes, perfect. Oh, not that button. Okay. when we had this wheel here, what they would do is they would turn this wheel like this. And when they turn the wheel, it is connected to the axle. I should really draw like spokes here so that you can see them. Here are the spokes of your wheel that are connected to your axle like this. Okay, so they would turn the wheel, and when they turn the wheel, basically if they turn the wheel a half turn, like if they turn the wheel, oh gosh, I actually want a marker because that'll show a little bit better. Oh no, this is so very bad. This is so very bad. I can't trace. I can do it, but it's just really hard. Okay. When they turn the wheel up a half turn, that turns the axle a half turn. But what you'll see is a half turn on a wheel is a lot bigger than a half turn on an axle because the radius is so much bigger. So your delta x is way bigger, which means that the force that you have to apply to accomplish that delta x is way less. So this made it easier for all of the children of the world to get water at the well, is because then they could just turn the wheel. When they turn the wheel, it turns the axle. A big turn on the wheel is a small turn of the axle, but it gradually brings the bucket back up. That is our fourth simple machine. Our fifth simple machine is a lever. Here's the idea. Suppose that you had to lift a box, but that box was very heavy. Now, one thing that you could do is you could take that box and you could lift it from where it is right now, which is right here. Oh, no, not like that. Oh, gosh. Embarrassing. Oh, my. Okay. You could lift the box from where it is now, which is right here, and you could lift it straight up to where you want it to be, which is right there. And you could do that. But if that box is heavy, that's going to be a big force that you cover over a longer distance, or you could use a lever. If you use a lever, well, then what you're going to do is you're going to apply a force, but this time you're going to apply the force to this end here. That force is going to be a force downwards. And when you apply that force downwards, it'll make your little box move upwards. Now notice, I go much bigger downwards, but I go very little upwards. That means I have a much bigger distance, but it makes it easier. I don't have to apply as much force. And this is the general concept of something like a dolly. A dolly makes it very easy to lift a box or something like that, is that it just has a little place where you lift a very short distance by pulling down a much bigger distance. And so it makes the job easier. Now let's take a look at a pulley. Now, actually, for this one, I kind of want to show you a few different sets of pulleys. So I'm going to see if I can move my computer over and see if we can make it happen. Actually, JK, my computer has no charge if you look down here. So I'm going to wait until the end of the video, and then at the end of the video, if I have some charge, then we'll go and look at our pulleys. Okay, but I'll just show you a picture here. Now, one pulley by itself is actually not that helpful for being a simple machine. One pulley by itself is actually not a simple machine because it doesn't really, oh wow, the green just exploded across the page. If this were a real piece of paper, I would really be sad right now, but luckily it's not a real piece of paper, so I can just undo it. Okay, I'm looking for the color black here. Okay, so one pulley by itself is not a very good simple machine. One pulley by itself, all that it does is it just changes the direction of a force. So suppose that I have a little mass that is hooked onto the end of a pulley, maybe something heavy, maybe something light, but you get the idea. Suppose that I have a little mass that is hooked onto the edge of a pulley like this. Okay, if I have a little mass hooked onto the edge of a pulley, and let's say that this mass weighs 2 newtons. Let's say that that's the weight of the mass. If I want to lift the mass, well then I would have to pull up on the mass with a force that is equal to its weight. And if there's no pulley here, then I would have to pull up for 2 newtons. And say that I wanted to lift it 10 centimeters, then I would have to pull up for 10 centimeters with a force of 2 newtons. But if I have a pulley, one pulley by itself is not a very good simple machine because it actually doesn't change the force or the distance. But what it does do is it does change the direction of the force. So what I would do is I would apply a force down And my force down would make the little mass go up. And so, again, the force is the same. Like, if that thing weighs 2 newtons and I pull down, oh gosh, I'm just leaving marks everywhere. One moment, please. Oh, see? How problematic. Just throwing green all over the page. You know me. Oh gosh, this is like really getting for serious. I might have to take a quick pause here. Wait, let me pause and fix this. Okay, wow, guys, it was good news that I paused because that literally took so long to fix. Okay, so I apply a force down and that makes this little guy go up. Now, this isn't a very good simple machine because in order to lift this guy, which is 2 newtons, I still have to apply a force of 2 newtons. And if I want to lift it 10 centimeters, I still have to pull down 10 centimeters. But what it does do is it does just change the direction of the force. However, where a pulley becomes a very helpful simple machine is when a pulley is no longer a pulley, but a system of pulleys, 2 pulleys like this. And we call 2 pulleys together a box and tackle. I don't know why we call it a box and tackle. A box and tackle sounds like something I want to bring with me when I go fishing. But that is not what it is. It's just 2 or more pulleys. Now here's where this gets helpful. Is because this 2 Newton, this 2 Newton weight is getting pulled down with 2 newtons, and it would say that it is experiencing, oh gosh, is this all going to happen to us again? Come on. Come on, we can do it. We can do it. Yes, we can. Please don't do what you did last time. Okay, I'm feeling relatively confident. Okay, so this thing weighs 2 newtons, except that it's not writing. 2 newtons. Oh gosh, okay guys, so sorry, give me 2 seconds. Okay, so gravity is pulling down on this guy with a force of 2 newtons. Well, this little guy would say, I'm being held up by 2 strings. And each of those strings are helping to support my weight. So one string is holding me up with a force of 1 newton. And the other string is holding me up with a force of 1 newton. And so this little guy here would say, I weigh 2 newtons and I have 2 strings that are holding me up. But here's the secret. It's all 1 string. It's just looped around double. If then I went to go to pull this thing, and we're going to change colors here. We're going to see how it goes. Let's try it. Everybody, you can do it. If I go to pull this string down, I have to pull down with a force of, well, however much tension is in the string, which is 1 newton. So I pull down with a force of 1 newton, and then I lift something that weighs 2 newtons. But here's the situation, is that even though I pull down with a force of 1 newton, because this string goes bloop, bloop, and it loops twice around, I have to pull it twice as far, because I have to pull it all the way for this distance and all the way for this distance. So when I pull, if I want to pull this guy up 10 centimeters, then I have to go 10 centimeters plus 10 centimeters. I got to pull 20 centimeters. So I increase my distance. I go twice the distance, but I pull with half the force. Meanwhile, my output, that's what I put in, my output, what this little mass experiences, is this mass would say, well, I got pulled with a force that is equal to my weight, and I went 10 centimeters. And so you can see here that this pulley, just like every other simple machine, trades force for distance. It says you pull with less force, but you're going to pull for longer. Now this is if I have a box and tackle with 2 pulleys, but I want to show you a box and tackle with 6 pulleys because I'm crazy. Okay, let's see. I think it's this one right here. Yes, there it is. Here's a box and tackle with 6 pulleys. So I have 1, 2, 3, 4, 5, 6. Let's look at our situation. This little guy, let's suppose that he still weighs 2 newtons. He still has 2 newtons of force pulling down on him. But he looks up and he says, I'm being held up by 1, 2, 3, 4, 5, 6 strings. And it's true that the weight of this block here, or the weight of this mass, is being supported by 6 different strings. Now, really, it's one string looped around 6 times. But for all this mass knows, it feels like it's being held up by 6 strings. That means that each string only has to hold up a sixth of the weight of this mass. If this mass has a weight of 2 newtons, and each string only has to hold up a sixth of that, then each string only has to hold up a third of a newton. Which means if I were to pull on this string, I would have to pull with the tension in the string. And the force of tension in the string that I would have to pull with is a third of a newton. So I'd pull with a third of a newton, but I have to pull through 1 pulley, 2 pulley, 3 pulley, 4 pulley, 5 pulley, 6 pulley. So if I'm going to pull this string, if I want this guy to go up 10 centimeters, then I'm going to have to pull for a distance of 6 times that. I would have to pull 60 centimeters in order for this little guy here to go 10 centimeters. So my force is small, but my distance is big. That's what I put in. Meanwhile, what I get out, my output, is what would happen without the pulleys. Without the pulleys, I would have to apply a much bigger force. I would have to apply a force of 2 newtons instead of a third of a newton. And I would have to go a much smaller distance. I would only have to lift it 10 centimeters instead of pulling for 60 centimeters. So here my force is 2 newtons, and here my distance is 10 centimeters. Do you see how in both cases, I get that my total amount of work done is 20 joules worth of work, here 2 times 10, here 1/3 times 60. In both cases, the amount of work done is the same, but that work is divided up differently between the force and the distance. If I have 6 pulleys, I do a sixth of the force and 6 times the distance. If I have 4 pulleys, you could probably guess, I would do a fourth of the force and 4 times the distance. If I had 8 pulleys, I would do an eighth of the force and 8 times the distance. So you can kind of see here how those ratios work. And those are all 6 types of simple machines. We have the inclined plane, or the ramp. Screws, which is basically just an inclined plane wrapped around a cylinder. Then we have a wedge, which is basically 2 inclined planes stacked back to back. A wheel and axle, a lever, and finally a system of pulleys, or a box and tackle. And that is all of our types of simple machines. Now let's take a look at some equations. Okay, ignore this ramp that I have drawn off to the side. It's going to be useful later. Okay, let's talk through our equations. We have 3 equations that govern our use of simple machines. Here's my first equation. My first equation is that if I have an ideal simple machine, then the amount of work that I put in should be equal to the amount of work that I get out. My input work should equal my output work. The force and the distance might be different for each one, but in the end, the amount of work that you put in should be the same as the amount of work that you put out. You just trade force for distance, but the total energy is the same. That's my first equation. Here's my second equation. My second equation is about what we call mechanical advantage. Oh no, I've left off the mechanical advantage, which we abbreviate as a capital M, capital A with periods here to show that it's abbreviation and that it's not mass times area. Mechanical advantage is a way of talking about how helpful a machine is. Some machines are more helpful than others. For example, 6 pulleys is more helpful to me than 2 pulleys, and 12 pulleys is more helpful to me than 6 pulleys because it does a better job of trading force for distance. So we talk about mechanical advantage as a measure of how helpful that machine actually is. The way that we calculate mechanical advantage is we calculate it by doing your output force divided by your input force. Mechanical advantage as a value has units that are nothing because it's a force divided by a force. The value of mechanical advantage will always be greater than 1. Here's why. The whole point of a simple machine is that you are making the input force, the amount of force that you have to put in with the simple machine there, less than the amount of force that you get out without the simple machine there. So your force in that you put in with the help of a simple machine, that should always, always, always be less than what you would have to do without the simple machine. And so your mechanical advantage should always have a bigger number on top than the amount of force that you put in. Let's talk about the mechanical advantage for a set of pulleys. If you had a set of 6 pulleys like this, and I asked you, what's the mechanical advantage of this box and tackle? You would say, okay, well, the mechanical advantage is the force that you get out divided by the force that you put in. The force that I get out, well, that is 2 newtons because that's how much force it would take to lift that little guy if I didn't have this whole pulley set up. The force that I put in this case is 1/3 of a newton. So my total mechanical advantage in this case is 6. This is true regardless of the size of the mass. Suppose that the mass was 1 newton. If the size of the mass was 1 newton, my output force would be 1 newton, my input force would be 1/6, and I would say I get 6 times as much force out as what I put in. And so that would be my mechanical advantage. If I had, you'll notice here, sorry, quick pause. You'll notice here that the mechanical advantage for a system of pulleys is equal to the number of pulleys that you have. If I have 8 pulleys, then my output force is going to be 8 times bigger than my input force. And so if I have 8 pulleys, then my mechanical advantage will be 8. If I have 2 pulleys, then my output force, how much I can lift, will be 2 times bigger than my input force. So my mechanical advantage will be 2. So you can see that for pulleys, you can easily find the mechanical advantage by just doing your output force over your input force, which will always end up being just your number of pulleys. Isn't that so very nice? Ah, we do love pulleys. Pulleys are just great. Let's go back to our equations. Work in is equal to work out, and this concept of mechanical advantage. Both of these are equations that we have for what we call ideal simple machines. Ideally, a simple machine isn't losing any energy. So over time, the amount of energy that you put in by pushing this up a ramp versus by lifting it straight up, that amount of energy should be the same. However, in real life, that's not really true. Because if I try to push this block up the ramp, well, I'm going to encounter some friction along that ramp. So suppose that I put in, I don't know, call it 3 joules of work. If I put in 3 joules of work into this block, but one of those joules has to go into overcoming the force of friction, then that means I will end up with my input work being 3 joules, but my output work will only be 2 joules. To talk about how good a simple machine is at using the energy that you put in, we talk about a concept that we call, actually I'm moving this down here, we talk about a concept that we call efficiency. We can calculate the efficiency of a simple machine by doing the actual output work divided by your ideal output work. Or we can calculate it by doing your actual mechanical advantage divided by your ideal mechanical advantage. Here's what we mean by actual workout divided by ideal workout. In real life, if I put in 3 joules, that's my work in. So what I should get out should be 3 joules, but that's not what I actually get out. I actually get out 2 joules. And so when I calculate my efficiency here, I would say my actual workout is 2 joules. The amount of work that I was supposed to get out was 3 joules because that's what I put in. And so my efficiency would be 2/3 here, or 66%. Now, if I wanted to write this equation a different way, I could also say that it's my actual workout, my output work, divided by the amount of work that I put in. Because ideally, the amount of work that I get out should be equal to the amount of work that I get in. So these two things are saying the same thing, since the ideal amount of work that I should get out should be the same as what I put in. So you could look at this equation both of these ways. Efficiency will always be a value that is less than 1. It'll always be less than 1. Because you'll always have less work out than what you were supposed to have. So sometimes we express it as a decimal, but you can actually also express it as a percentage. You can express it as a decimal place or as a percentage, and either one is totally great and totally acceptable. Outside of being a percent, efficiency actually doesn't have any units because you would have joules on top and joules on bottom. Let's go ahead and try a practice problem. Suppose that I asked you for this ramp. Suppose that I had a, what color? We'll go purple. Suppose that I had a mass of size M. Oh no, is it going to do it? Is it going to be okay? Oh, I'm on eraser mode. That's why it's not writing. Everything makes sense now. Suppose that I have a mass of size M. And I want to lift that mass up a distance of delta H. And to do it, I'm going to take that block up a ramp that has a length of L. Here's the question, is what force would be required to push the block up the ramp? Now you could do this the old school way by drawing a free body diagram of the force on this ramp, of the forces acting on this guy, and you would draw its weight component down, and then you would have to break that down into the X component and the Y component, and you would say the amount of force that it takes to lift it is equal to the X component of the weight, and you could do it that way. Or you could do it using simple machines. Here's what you would say. You'd say if we have an ideal simple machine, then the amount of work that you put in to slide it up the ramp should equal the amount of work that you get out. My input work would be the force that I put in times the distance that I put it in for. My output work would be the force that I would apply without the simple machine times the distance that I would have to go without the simple machine. Now, I plug in here things that I know. The force that I have to put in, that's what I'm looking for. That is the question mark of the day, is how much force do you have to put in? So that's what I'm looking for. I know that the distance that I have to go is going to be a length L, because that's how far I am actually pushing the block up the ramp. My output then, well, that's how much force it would take if I just lifted it straight up, and that would take its weight to lift it straight up. And the distance I would have to go in that case is delta H. Now we know that Fg is equal to mg, so we can replace that. Rearrange here to find F in my input force, and you would get mg delta H divided by L. And that would be the size of my input force here. Now suppose that I asked you, hey cool, thanks for finding the amount of force that you would have to apply, but now here's my question, is what's the mechanical advantage of this ramp? You would say, well, I could find that, no problem. You'd say mechanical advantage is my output force over my input force. And you'd say my output force, well, we already talked about that. That would be mg, because that's how much it would take to lift it if the ramp wasn't there. My input force, I just calculated it, is mg delta H over L. Well, nice. These two things cancel out, so those just go away, and you can algebraically rearrange a little bit to get that the mechanical advantage of this ramp would be L over delta H. And that gives me my mechanical advantage here. Now, before we move on, does it make sense to you that the mechanical advantage of this ramp would be equal to L over H? Think about it for a quick second. Here's what you should be saying. As this ramp, if this ramp has the same delta H to do, but it gets longer and longer and longer and longer, well, as it gets longer and longer and longer, this ramp is going to get shallower and shallower and shallower. So the amount of force that I would have to put in would be less and less and less and less, because the longer the ramp is, the less hard that I have to push it, because it's a less steep ramp. And so you'd say, yes, this makes sense, that the longer the ramp in comparison to the height, the easier it is to push it, and the easier it makes my life, and so the greater the mechanical advantage, since a mechanical advantage is just a measure of how much easier a simple machine makes your life be. And that is pretty much all for today, folks. Today we talked about the 6 types of simple machines. You do need to know the 6 types of simple machines. We talked a little bit about mechanical advantage and how the work in is supposed to be equal to the work out. We talked about efficiency. We did a quick practice problem. And we went through each of the simple machines, and we talked about how for each one, it actually trades force for distance. It increases the distance but decreases the force that you need to apply in order to get a job done, hence making the work a little bit easier. And that is all for today, folks. I do hope that you have just a wonderful rest of your day, and I'll see you next time. Bye, good people.